Welcome to this video on the Shockley-Queisser efficiency. The Shockley-Queisser efficiency has been recognized as one fundamental efficiency value for solar cells and has a high importance today still, 60 years after it was first published. And in this video I want to introduce to you what the Shockley-Queisser argument it is and how it is a paradigm shift to calculate the efficiency. Let's start with a quick review because we are going to reuse part of what I already told you in other videos. And that is, first of all, the Trivich and Flinn efficiency model considered the situation where we have incident radiation onto a semiconductor. The semiconductor is described by a band gap, e.g. between the valence band and the conduction band. And it is considered that every photon with a band gap, with an energy larger than the band gap energy is absorbed. So all photons with a band gap exceeding the band gap energy are absorbed, form an electron-hole pair, and then the electrons thermalize quickly to the band edge. Also the holes thermalize to the band edge. So the Trivich and Flinn efficiency model argued we absorb all photons with energies larger than the band gap energy, and each of these photons contributes the band gap energy to the output power. The Trivich and Flinn efficiency model then can be calculated as shown here again. So we see here the solar spectrum, and of this solar spectrum, only wavelengths that are shorter than the band gap wavelength are absorbed. So here the band gap is assumed to be at 1 electron volt, so at around 1240 nanometers, and then all wavelengths for all photons with wavelengths shorter than this value are absorbed, while all photons with wavelengths longer than this value pass through the semiconductor as their photon energy is smaller than the band gap energy. And so based on this, we can calculate what the absorption is, but then we also need to consider the thermalization effects, and that is that each photon contributes only the band gap energy. So if we are right at the band gap, the photon energy is equal to the band gap energy, and we have 100% efficiency for these photons. But if we are, for example, at a wavelength corresponding to around half of the band gap energy, photon energy around half the band gap energy, then we see that only 50% of the energy can be extracted as electricity. And this Trivich and Flinn efficiency we described in the terms given here. So we have the incident power is given by summing up the spectral irradiance, and the extracted or external electric power that is available is at maximum then given by the sum of the spectral irradiance up to the band gap wavelength, to the wavelength corresponding to the band gap. And we have to also then consider that we have to multiply with this factor Eg to E photon. That is that each photon contributes only one band gap energy equivalent. So this term up here is actually the same as saying we calculate the absorbed photon flux, that is the number of photons, which would be the spectral irradiance divided by the photon energy, and this photon flux that is absorbed, phi absorbed, is multiplied with the band gap energy Eg. So this is the Trivich and Flinn efficiency, and then we saw that Prince already argued in 1955 that this is not the whole story, because you will connect the semiconductor solar cell to an external load. And this means that if you have an external load here, you cannot operate the solar cell at the open circuit voltage that is at the band gap energy multiplied by the elementary charge, divided by the elementary charge. But you also have to consider that you have a certain current voltage characteristic, while if a current is flowing, the voltage is smaller than the open circuit voltage. And this was described by the fill factor by Prince, where the fill factor is determined by the voltage at the maximum power point times the current at the maximum power point divided by the open circuit voltage times the short circuit current. So the Prince efficiency is always lower, or at most equal to, it would be equal if the fill factor is 1, it would be equal to the Trivich and Flinn efficiency, but for all fill factors below 100%, the Prince efficiency is lower than the Trivich and Flinn efficiency. And in order to calculate what the maximum power point is, you need to have some electric model for the semiconductor solar cell. And the simplest model is to assume that the solar cell behaves like a diode that has this photo current source in parallel with it. And in this, if you have this kind of model, then the total current I is given by the photocurrent that is due to the photon flux onto the solar cell minus the diode current here, and the diode current is given by the well-known diode equation, saturation current times E to the voltage U divided by the ideality factor N times the temperature voltage UT minus 1. So in order to use the Prince model and to calculate what the efficiency is, you need to know this diode equation here. And actually in this diode equation, the saturation current IS and also the ideality factor, those are experimental values. So when in 1955 this paper was first published, the saturation current was still a lot higher than it is experimentally today. So this value has been improving in terms of it has been reduced, and that improves how square the current voltage characteristics are, and it increases the fill factor. So in that sense, this can be improved experimentally. But the question is there a fundamental limit? To what value can the saturation current IS be improved? So what Shockley and Queisser said, this is all correct what the others did, but it's not really the fundamental limit. It's an experimental limit. It's determined by what is the saturation current that is minimally appearing in the solar cell. So the question, of course, of the fundamental limit is how small can you make the saturation current, and that would determine the ultimate efficiency. So Shockley and Queisser set out to find out what is the fundamental limit for this saturation current here, and therefore the fundamental limit for the efficiency. And for this purpose, Shockley and Queisser considered a thermodynamic principles argument. So this was really a paradigm shift. Before, the authors considered certain experimental IV characteristic, calculated fill factors, then knew what for this type of solar cell the maximum efficiency is. But what Shockley and Queisser said, let's look at it from a thermodynamics point of view in order to find the fundamental limit. And first of all, if you look at it from a fundamental thermodynamics point of view, then we know that in a steady state condition, a radiation equilibrium is necessary. That is, if we have a certain body in an equilibrium, it means the radiation that is incident onto the body is the same as the radiation that is, or the energy that is leaving the body. So therefore, Shockley and Queisser first considered this situation where we have a black body radiator that is surrounding a solar cell, a semiconductor solar cell with a given band gap at a temperature of 0 Kelvin. So absolute temperature of 0 and a black body. And this actually I drew it as a circle here. I tried to show it a bit differently. You have to imagine it like a sphere. So the sphere, the black body sphere, is completely surrounding the solar cell shown here that is at 0 Kelvin. So we have a material that is completely surrounded by black body radiation. And if we have this situation, then we can extract from the semiconductor solar cell a certain power that is given by current I times voltage U for a matched consumer. A matched consumer means we have chosen a consumer such that we are at the maximum power point, and that is a matched consumer, then a matched load. So we assume we have a matched load that gets the electricity out, and what is incident onto the semiconductor is all of this black body radiation at 6,000 Kelvin. Now, if you look at this situation, you already see it doesn't quite resemble our situation on Earth, because indeed we do not have black body radiation coming from all directions, but the sun is only in a certain range of the sky. So in order to calculate this scenario, we have to consider that the sun is not everywhere, but only at a certain range of the sky. We can assume that the sun is a black body with 6,000 Kelvin. And in order to consider that the sun is not everywhere, but only in a certain area, what is done typically is to calculate the solid angle of the sun under which we view the sun. And this solid angle here is called omega s. So the omega s is the solid angle of where the sun is compared to the whole surrounding areas of the solar cell. So of course, if we now have only part of the sky sending out radiation at 6,000 Kelvin, then this will be significantly less energy that can be extracted. And so in thermal equilibrium, we also have to consider now, though, that the semiconductor is not at 0 Kelvin, because on Earth we have a temperature of approximately 300 Kelvin. So in thermal equilibrium, the second thing we need to change is that the semiconductor has a certain temperature also. So for going from this situation where we have a black body radiator on all sides of a solar cell at 0 Kelvin and extracting the maximum efficiency, to get a realistic image, we have to consider that we have a sun only in a certain range of the sky, and that our semiconductor has a temperature that is in equilibrium with the surrounding, for example, at 300 Kelvin. Of course, the thermal equilibrium could also be different, so this temperature could be higher or it could be cool, so other things could happen. But in general, we have here the semiconductor at around 300 Kelvin. And this then means that if the semiconductor is at 300 Kelvin, it is also a black body. So also the semiconductor here will send out radiation, and I showed this a bit with this red frame, which means the semiconductor is actually emitting thermal radiation in all directions. It's like a piece not that hot, but of a hot material at 300 Kelvin and emitting in all directions. So this black body radiation of the solar cell at a temperature Tc, T cell of, for example, 300 Kelvin, is a thermodynamic fundamental loss mechanism. So if we have our cell at room temperature, then it means it will radiate. And this will be a loss because the radiation will not be available for the circuit here to drive the electric circuit, so it will not be available as electric power. So what Shockley and Queisser say is that the losses we consider are only these thermodynamic radiation losses, so the thermodynamic equilibrium with the surrounding area. So the losses are the thermal radiation of the solar cell at 300 Kelvin. And they say if we want to have a semiconductor that is absorbing light of the sun, that means that also we have to have radiative losses due to electron and hole recombination. So the fundamental principle of what is happening in the semiconductor is that due to incident radiation from the sun, we get an electron-hole pair. But if we have electron-hole pairs, that means they can recombine also. And this recombination then is by Shockley and Queisser set equal to the black body photon flux. So they say that the photon flux of the black body at the temperature Tc multiplied by the elementary charge Q, that is equal to the saturation current per area, or you multiply it by the area as well, and then you get the total saturation current IS. So they say do not do experiments in order to find out what your experimental IS is at the time, but let's consider what is the minimum value of the IS, and the minimum value of the saturation current of the diode would be if all the saturation current is caused or is related to the thermal radiation of the solar cell at the given temperature. And that would be the minimum loss that we can have. So this is the paradigm change that Shockley and Queisser said, let's only consider the thermal effect. So we only consider that the sun is sending out radiation to the solar cell, and the solar cell is also sending out radiation. Only let's take the balance of these two effects and the extracted electric energy. So in that sense, they call it a detailed balance between the different mechanisms, the incident irradiation, so the incident photon flux, the photon flux emitted by the semiconductor, and the electron flux that we then have as electricity here. Actually, this paper goes quite a bit further. They also consider other effects. They consider other loss mechanisms. How will they act into this balance? They also consider what happens if not all of the photon flux is absorbed, so if we don't have unity absorption. And all of these losses will make it worse. I mean, if the semiconductor does not absorb all of the photon flux, then of course the efficiency is lower because less of the photon flux that is incident is utilized. If we have additional loss mechanisms in the semiconductor, for example, due to other recombination mechanisms, also this makes the situation worse, so the efficiency is lower. And in that sense, this situation I described here, where we only consider the effect of the radiation and not any other loss mechanisms or non-unity absorption, is the highest efficiency that can be achieved. And therefore, this is the limiting Shockley-Queisser efficiency. And in the paper, you can look at everything else that might happen and what influence it has. Okay, so then if you have the saturation current, then you can go on in the Shockley and Queisser efficiency model the same way that as the Prince efficiency model is going. So that means you have then this diode equation here as the best case, so no series resistance. The shunt resistance is infinity, so you don't have any resistance effects. That's the ideal case. You plug the saturation current into this ideal case IV characteristic for a diode with the I photon in parallel, so with the I photo, the photo current in parallel. And then you can calculate from this what the IV characteristic is and calculate the fill factor, and then similar to the Trivich and Flinn efficiency, calculate what part of the photons is absorbed based on the band gap of the semiconductor. So everything that is happening after this is the same as what Prince and Trivich and Flinn did, and that's why I introduced that again at the beginning of the video. Okay, so with this introduction, in the next video we will go ahead and do a calculation and see what it means. So what is the Shockley and Queisser efficiency that is obtained as the ultimate efficiency? Thanks for watching.